Hi, hello everyone. This is Nepalidi sir from ANR Academy. Today I am here with you to share about periodicity of a function. The definition of periodic function mathematically f of x plus p. Suppose if it is equal to f of x, then p is known as period of the function, and the fundamental period for which p must be least positive real number. This is the mathematical definition of periodicity of a function. The meaning here, f of x equal to, since f of x plus p, the functional value of this function that repeats at x plus p again. So the function repeats in the regular intervals implies the function is periodic function, and length of that regular interval is known as period of that function. For example, if I select f of x equal to sin x, we know the graph of sin x in the interval 0 to pi. This is the graph. Next, it is in the interval pi to 2 pi. On continuation, here it is 3 pi x value. Next, here it is 4 pi. For all negative values of x also it is defined. See here, the graph of f of x at origin, it indicates functional value 0. The same value you have at x equal to 2 pi, and in the regular intervals it repeats the values. Up to 0 to 2 pi, whatever the graph you have, the same graph repeats in the next regular intervals in this way, so that 2 pi is period of the function, and also it repeats functional value at 4 pi. So 4 pi also period. So period is either 2 pi or 4 pi or 6 pi and so on. Remember, but the fundamental period is least positive real number. That is 2 pi is the fundamental period. Here f of x also repeats at pi, but that is not period of the function. Why? Because up to 0 to pi functional value positive, from pi to 2 pi functional value negative. Wherever the graph repeats in the regular intervals, nothing but 0 to 2 pi, whatever the graph you have, the same graph that repeats again from 2 pi to 4 pi. This regular interval length, that is known as fundamental period of the function. The gap here you have 2 pi, and here 4 pi to 2 pi, the difference you have 2 pi. So that 2 pi is period of the function, and that is clearly least positive real number from period of f of x. And trigonometric functions sin x, cos x, tan x, cot x, secant x and cosecant x, they are periodic, remember. Why? Because if you observe the graphs of trigonometric functions, they repeats on regular intervals. And one more special function is there, that is fractional part of a function. F of x equal to fractional part of x. You know the graph of fractional part function. Also it repeats in the regular intervals. You know the graph. This is the graph of fractional part function, and it repeats at 1, 2, the same graph repeats at 3 and so on. but the least positive real number here 1, so that period of this function is 1. We know that the graph of sin x, cos x, let us see the graphs. You know the graph of sin x and the graph of cos x and tan x. After that we will discuss cot x, and then we go for graph of secant x and cosecant x. Just now we discussed about the graph of sin x, up and downs, 0 to pi, pi to 2 pi, 2 pi to 3 pi, and so on. And here the graph repeats at x equal to 2 pi. Next, cosine graph. Like wave, and the graph repeats at 2 pi here. Whatever the graph you have in the interval 0 to 2 pi, the same graph that repeats at 2 pi. See here, that repeats again here, so that period is 2 pi. Next, you know the graph of tan x. Tan x graph strictly increasing in the interval minus pi by 2 to pi by 2, and then repeats. Here the graph which is at origin, the same graph repeating clearly at pi, so that period of the function is pi in this case. Next, graph of cot x. You know the graph of cot x strictly decreasing in the interval 0 to pi. The same graph repeats. And here, since the graph repeats at pi, pi is period of this function. Here pi is period of this function. Here 2 pi is the period of the function, and here 2 pi is the period. Observe tan x and cot x. Whatever the graph you have at origin, the same graph repetition starts at x equal to pi. Due to that reason, period of the function is known as pi. Next, cot x. See the graph of cot x. First observe the graph nearby origin. Up to 0 to pi decreasing graph you have. The same graph that repeats now from pi to 2 pi. And then 2 pi to 3 pi, again it repeats. Pi, 2 pi, 3 pi, they are all periods of the function, but the fundamental period is least positive real number, that is pi in this case. Here it is of pi. Next, secant x graph. It is reciprocal of cos x. Reciprocal graph of cos. Whatever the graph you have in the interval minus pi by 2 cos x, that reverse. You have to draw in the reverse manner. Next here, and then it continues. This is the graph, and let us observe the graph nearby origin. It is increasing up to 0 to pi by 2. In the interval 0 to pi by 2 it is increasing. Next, from pi by 2 to pi also increasing. Next, the graph which you have at origin, the same graph again it repeats here. next continuation, this one is the graph. So in this way it continues, and up to here it is pi by 2, next pi, 3 pi by 2, and it is 2 pi. So the graph repetition starts at x equal to 2 pi, and it is clearly least positive real number, so that 2 pi is period in this case. Next, the graph of cosecant x. It is reciprocal of sine. Sine graph in the interval 0 to pi by 2 positive. Reverse of sine you will get. This is the graph of cosecant x. Whatever the graph you have nearby origin, the same graph where it repeats, observe from the graph, this one and this one, and after that here the repetition starts. The same graph repetition starts here at particularly x equal to 2 pi. Due to that reason, here period of the function expressed as 2 pi. These 6 trigonometric functions are periodic, remember, and you have another function, a special function called as fractional part of a function. Fractional part of x, that is defined by f of x equal to x in braces, and the graph in the interval 0 to 1, this one is fractional part graph. Next, from 1 to 2, this is the graph, and in the interval 2 to 3, this one. It is also defined for negative values of x. 1, 2, 3 and so on. They are periods of the function, but the least positive real number is known as fundamental period, and fundamental period of this fractional part function is clearly 1. Let us discuss the properties. Remember, fundamental period is least positive real number. And next point, if suppose period of the function f of x is p, then period of f of x plus constant, f of x minus constant, and constant into f of x 1 by f of x, they are of same period p. Also the same period p, remember. And next point, if suppose if f of x is of period pi, period not pi, p, then f of kx is of period p divided by modulus k, remember. And another point, if f of x is periodic, then its derivative f dash of x also periodic, remember. and also I am going to write next properties. Suppose that if there is a function f of x which is algebraic combination of different types of functions, suppose f1 of x plus f2 of x divided by f3 of x multiplied by f4 of x. A function f of x which is obtained by applying algebraic operations like addition, subtraction, multiplication, division with different types of functions f1, f2, f3, f4 and so on. Then period of the function, in this case period of f of x is, that is LCM of individual periods, LCM of individual periods of given f1 of x, f2 of x, f3 of x and f4 of x. And also here you have to remember LCM formula for fractions. Suppose if you need to find LCM of P by Q, L by M, R by S, there are three rational numbers. Suppose if you need to find LCM of these three, then you have to use this formula. LCM for numerators P, L, R divided by HCF of denominator parts Q, M and S, remember. Suppose if you have individual periods, they are rational numbers, then remember that this is the formula for calculating LCM. And suppose if you got LCM of one rational number and one irrational number, it is impossible, remember. If both irrationals, then LCM is possible. If one is rational and the other is irrational, LCM not possible. You have to remember all these things. Let us discuss the previous properties. Fundamental period is given as, that is least positive real number. Yes, by the previous graphs it is very clear that there are so many periods. The graph repeats at 1, 2, 3. We know the fundamental definition, f of x plus p equal to f of x, right? Here f of x plus 1, f of x plus 2, also f of x. I can write f of x plus 3, also f of x. But the least one is here 1, that is the period of the function. Next, observe the second property. Period of the function f of x is p, suppose, then period of f of x plus k, f of x minus k, k into f of x and 1 by f of x also p. Yes, let us see an example. You know the graph of sin x. Then let us discuss the graph of sin x plus k or minus k, and suppose something multiplied by sin x and reciprocal of sin x. Let us observe all the graphs. If the period of the function sin x is 2 pi, then the period of sin x plus k 2 times of sin x and reciprocal of sin x also, from this property you have to write 2 pi. Let us see the graph. You know the graph of sin x, and the graph repeats at x equal to 2 pi, and this is known as fundamental period. When you have sin x plus some constant, suppose that constant 1, what happens? Sin x value always lies between -1 to +1. When you add 1, sin x plus 1 lies between 0 and 2. The graph of sin x plus 1 whose range 0 to 2. You will get in this way the graph. And observe, whatever the graph you have at origin, the same graph repeats here. For example, another page I am going to select. Sin x and the graph of sin x plus 1. You know that sin x graph lies between, its range lies between -1 to +1. When you add 1 here, then here you have to add 1 and here you have to add 1, so that we get 0 to 2. And the graph of sin x, this one is the graph and its fundamental period, you know that 2 pi. Next, the graph of sin of x plus 1. This is, yes, sin x plus 1 graph. Suppose x value 0, then it is 1. Sin 0, 0 plus 1 become 1. Next, suppose x value pi by 2. Sin 90, 1 plus 1 goes to 2. Next, if you write pi, sin pi 0, 0 plus 1, again it reduces to 1. Next, if you write 3 pi by 2, what happens? Sin 3 pi by 2 value, -1. So, -1 plus 1, that become 0. Next, if you write 2 pi, sin 2 pi value 0, 0 plus 1, again it is 1. So, the graph repetition starts again at 2 pi. If you continue this graph, then what happens? It goes like this, right? So, the graph repeats at 2 pi. So, by the second property, if f of x is of period p, then f of x plus k also of period p. Next, example 2 sin x. Suppose I am going to select the graph of 2 sin x. You know that sin x value lies between -1 plus 1, multiplying with 2. What happens? The graph lies between -2 to +2. The range of the graph changes. You will get the graph in this way. When x equal to 0, 2 sin x also 0 here. Next, when x equal to pi, 2 sin x also 0. Next, here 2 pi. Suppose if you write x value 2 pi, again 2 sin x is 0. That is, the graph crosses x-axis same points of sin x, at same points of sin x, but only the difference in the range. So that here again the graph repeats at 2 pi. So when you multiply some constant to the given function, the period of the function does not alter, remember. Next, addition or subtraction or multiplication. Next, reciprocal. You know that reciprocal of sin x, that is cosecant x. And by the trigonometric graphs, it is very clear that cosecant x written as reciprocal of sin x. If the period of the function sin x is 2 pi, then it's reciprocal also of period 2 pi by this example. Next property. Next you have, if f of x is of period p, then f of kx is of period p by modulus k. Let us see an example. I am going to select sin 2x. Suppose f of x is sin x, f of kx sin kx. Let us suppose the value of k equal to 2. Then f of 2x become sin 2x. Suppose if it is of period p, that is 2 pi, then the period of sin 2x must be by this property p by modulus k, nothing but 2 pi divided by coefficient of x with modulus sign. So it must be pi. Let us observe the graph. You know that this is the graph of sin x. And now I am going to draw the graph of sin 2x. When you write x value 0, output also 0. When you write pi by 2 x value, if you substitute x value pi by 2 here, it becomes sin pi. Sin pi again 0. So the graph repeats. The graph shrink in this way. Next, you will get, when you write x value pi, sin 2 pi also 0. When you write 3 pi by 2, again sin 3 pi 0. Next, so that here the graph shrink towards x direction, and clearly it shrink k units. And the repetition here, for this yellow colored, you have the repetition at x equal to pi, so that period of the function is clearly pi, remember. Next property, if f of x is periodic, then its derivative also periodic. Yes, you have trigonometric functions along with a special function called as fractional part function, and if you observe the derivatives of all trigonometric functions, again trigonometric, so that they are also periodic. Next, for special type of function, that is fractional part of x, that is piecewise function in the regular intervals, it is in the interval 0 to 1, it is x. In the interval 1 to 2, it is x minus 1. In the interval 2 to 3, it is x minus 2. The function is defined piecewise, and its derivative f of x equal to x implies f dash x is 1. F of x is x minus 1 implies f dash x again 1. X minus 2 derivative again 1. So its derivative become derivative of this, it is clearly 1. And it is constant function. Derivative f dash of x here, in all the cases, it is 1 clearly. When the function is constant function, you know that constant function, nothing but that is indicating a line parallel to x-axis. Y equal to constant is a line parallel to x-axis. But here, it is not defined at, in the regular intervals, it is discontinuous at integers, but defined at x equal to 1 also. So clearly it is y equal to 1 after differentiation. The graph repetition starts very next number of 0, but we can't say that particular number. The graph repeats at 1, graph repeats at 2, at 1 by 2 also it repeats, at 1 by 4 also it repeats. nearby 0, very next number of 0 it repeats, but very next number of 0 that must be positive real number, and we can't say perfectly. It is periodic, but its period is not defined, remember. The function is periodic, but the period of the function that is not well defined for constant function. Next, here you have a function which is obtained by applying algebraic operations to different types of functions. In such cases, you have to find LCM of individual periods of f1, f2, f3. For example, if I choose f of x as fractional part of x by 2 plus fractional part of 3x whole divided by fractional part of 4x. This is the question. In such cases, you have to find LCM. First, fractional part of x is of period 1, but you have multiple 1 by 2 here. So 1 by 1 by 2. Next, fractional part of x period 1, its multiple 4, you have to write in the denominator part by this property. When x is multiplied by k, p by k is the period. So here multiple 1 by 2, and here 3, and here 4. 1 by 3 here. So that 2 by 1, 1 by 4, 1 by 3. LCM of these numbers gives the answer. That is, here LCM of numerators 2, 1, 1 and highest common factor of 1, 4, 3 in the denominator part. LCM of 2, 1, 1, that is 2. HCF of 1, 4, 3, highest common factor of 1, 4, 3, that is 1, so that it has the period 2. Another question. Suppose that if f of x equal to mod sin x plus modulus cos x, then period of the function f of x. Option A, suppose pi. Option B, pi by 2. Option C, pi by 3. Option D, 2 pi. Suppose this is the question. See, mod sin x, mod cos x. Those graphs I am going to draw. This is the graph of mod sin x, and this one is the graph of mod cos x. And the graph repeats at pi. Here the graph repeats at x equal to pi. Now LCM of individual periods pi comma pi, that is clearly pi, both irrationals pi comma pi. If the numbers both irrationals, LCM is possible, and the LCM of pi comma pi is pi. Yes, it is period of the function, but not fundamental period. Remember, fundamental period must be less than LCM of individual periods. Here you have the property LCM of individual periods, and there is a note. Here period is okay, But to get fundamental period, sometimes it is fundamental period and sometimes it is not the fundamental period. Maybe the fundamental period is less than LCM of individuals. Remember, let us see this. Here in the previous case, 2 is LCM of individuals and that is fundamental period of the function f of x. But see this question, the basic definition, if f of x plus p equal to f of x, then p is called period. In this case, if you write f of x plus pi, this is true, it is also period of the function. But you have to cross check whether there is another least period in the given option, that you have to verify. Let us see first whether it is period or not. F of x plus pi, that is modulus of sine of x plus pi plus modulus of cos of x plus pi, sine 180 plus theta, again sine theta, due to modulus again it is mod cos x, and hence you got f of x. I can say that here pi is period, but may or may not fundamental period, remember. So due to that reason, we have to cross check the least value of pi, whether it is period or not, and I am going to cross check whether pi by 2 is fundamental period or not. F of x plus pi by 2 I am going to calculate. Suppose f of x plus pi by 2, then you have to write sine of x plus pi by 2 with modulus sine plus cos of x plus pi by 2 with modulus sine. And now f of x plus pi by 2 become sine 90 plus theta, that is cos theta, so that mod cos x, and here it become mod sin x, and clearly it is f of x. Not only pi by 2 is also period. In the previous case we got f of x plus pi also f of x. And what we discussed, if f of x plus pi equal to f of x, you can say pi as period but not fundamental period, so that you have to cross check whether the value is less than pi or not. Yes, you got pi by 2 also period of the function, and it is least positive real number. No other number gives the same function f of x when you put in place of p other than pi by 2. We can't get the function f of x. Only the least positive real number, here in this case f of x plus pi by 2. In the examination you have to cross check, this is period, it is also correct, but whether the less than pi, is there any periodicity or not, that you have to cross check. 2 pi is more than pi, so you have to eliminate the last option. You have to cross check pi by 2 and pi by 3. When you write pi by 2 only, sine changes to cos, cos changes to sine. But when you write pi by 3, sine x plus pi by 3 along with modulus, and here cos x plus pi by 3 along modulus we get, and on simplification it doesn't equal to f of x. So the least one is right answer. Both pi and pi by 2 correct, but the fundamental period is pi by 2, remember. Next, suppose that if you have sin x whole square, sin x whole power 4, sin x whole power 6, then what is the period? Square quantity always positive, and you will get period pi, remember. Next, sin cube x, sine power 5x, odd powers. Both positive and negative exist and period must be 2 pi. In the same way, the same applicable for cosine function, secant and cosecant also. Next, tangent. Whether it is even or odd, whatever it is, tan and cot both, cot square, cot cube and cot power 4x and so on. Whatever you have, the period is pi, remember. And modulus sin x, modulus cos x, modulus tan x, modulus cot x, modulus secant x, modulus cosecant x. Sin x, mod sin x is of period pi, remember. Mod cos x also pi, mod tan x also pi, mod cot x also pi, mod secant x and modulus cosecant x also pi. Modulus of trigonometric functions have the same period pi. For sine, cos, secant and cosecant, if you have even exponent, then period pi. If odd exponent, both positive and negative will get, therefore period 2 pi, remember. And for tan and cot, if the exponent is any natural number, then the period of that function is pi. And we will discuss functional equations whose periodicity in the next session. I hope you understand the fundamentals of periodicity of the function. Thank you so much.